It's my pleasure to introduce David Urbanik from the University of Toronto. Thanks for accepting our invitation, and he's going to tell us about algebraic cycle loci at the integral level.
Thank you very much. Thank you very much for the invitation. So let me roughly explain the kind of problem that I'm going to be considering. The general setup that I want to think about is where we have a smooth projective family of some kind that's defined over a subring of the complex numbers. So what I'm thinking of here is we have some projective space defined over R, which is this subring over of the complex numbers. You write down some algebraic equations, projective algebraic equations with parameters as coefficients. And everything is going to be defined over R, which means that the parameter space and the total space are defined with algebraic equations with coefficients in R. And the kind of thing that I want to think about is in the particular case where R is something like the ring of integers over a number field. So we can specialize this family to, let's say, a complex algebraic family, and we can also specialize it at some kind of prime to a family defined over a finite field. And what I want to talk about is I want to think about algebraic cycle loci in the parameter space S. So what do I mean by that? I mean something like, well, let's say that there is some locus in S, and this could be a locus in characteristic 0. It could be a locus in positive characteristic, just some closed subscheme of S over which we have some family of algebraic cycles. And what I mean by this is just there's a closed subscheme of the total space that lies over this subscheme in the base, this Z. And it's going to induce all sorts of cohomology classes in the various cohomological realizations of the cohomology of the fibers of our family F. And I want to understand the situation. I want to understand what kinds of non-trivial such loci can we get. So what do I mean by that? Well, of course, there are some algebraic cycles that are going to lie over all of S. And there are some that are maybe only going to lie over a point. And I want somehow the ones that are positive dimensional in some maybe cohomological sense. And so let me make that precise. So the first way I'm going to make that precise is I'm going to just think about the complex algebraic setting. And in this case, the sort of phenomenon that I'm talking about is well studied using the language of Hodge loci. And so to introduce that, let me just recall some background from Hodge theory. If you look at any point, complex point in the parameter space now, and you look at the Betty cohomology of some fiber, let's say in degree 2k, then that Betty cohomology is going to admit a Hodge decomposition. This is a decomposition. One way of thinking about it is using, for example, topological complex de Rham cohomology. The different subspaces are then given, they have certain representatives in terms of certain anti-holomorphic and holomorphic harmonic forms. Essentially, there's this decomposition, this complex decomposition of the Betty cohomology, which depends on the complex structure of the fiber above the point S. And so the idea is that somehow, if you look at this family, which is typically topologically trivial, like if it's the base is smooth and everything inside is smooth, it's a topologically trivial family. So the Betty cohomology doesn't vary, but this subspace decomposition on the Betty cohomology does vary. And this subspace decomposition is what I'm calling a Hodge structure. And one way that you understand this kind of non-triviality condition is that these fibers Y sub S define rational classes in the cohomology. That's just a kind of topological fact because they're topological, they're topological classes, but they also define a class in this middle piece of the Hodge subspace. And the Hodge conjecture, this kind of famous problem, in fact, that predicts that all rational classes in the middle piece come from algebraic cycles in this way. So that's one way we can understand sort of cohomologically what these algebraic cycles, these families of algebraic cycles are giving us. And then to give an interpretation of what I mean for such a family to be non-trivial, I can then use monodromy. So I can look at the fundamental group of Z, which is in this setting, I'm thinking of it as a complex algebraic subvariety of S, which is also a complex algebraic variety. And what you can show is that this class, this vector V that's being induced by the fiber Y sub S, that class is actually fixed by a finite index subgroup of the monodromy group of Z. And this comes from the fact that there's a natural bilinear form on this cohomology. Essentially, it comes from cup product. And that bilinear form is preserved by monodromy because it's a topological thing. So as you identify topologically the fibers and you go around loops, the bilinear form is preserved. And it's also positive definite on the space of all Hodge vectors. And so you can show that, you can only act, only a finite group can preserve this data in this way. And so it means that the monodromy group has to act through a finite group. And so a finite index subgroup of it will fix the vector V. And so what I can then say is that this family is a kind of interesting family, a family we want to study if no subgroup of the monodromy on all of S fixes, no finite index subgroup of the monodromy on all of S fixes this same class. So the idea is that somehow when you restrict to Z, the monodromy is actually getting smaller, and it's getting smaller because there's this extra algebraic cycle class. And so this is one way that you can kind of detect that you have here a family of algebraic cycles which isn't present over all of S. And I'm also going to require, when I talk about these loci Z, that the monodromy on Z is actually infinite. It is very interesting to study the question where there's algebraic cycles that are sort of isolated at individual points where there's no monodromy at all, but that question is sort of much harder. So the kinds of loci, algebraic cycle loci, at least in the complex algebraic case that I want to talk about, are ones where there's less monodromy on those loci than there is over all of S, but there is at least some monodromy. It's not just like a finite monodromy group. Okay. And so when we start talking about these loci, one of the things that you learn from Hodge theory is that, at least in the setting that I've set up, there's really kind of three types of things that can happen. And these types of things are controlled by what I'm going to call the level of the associated variation of Hodge structure. That's a technical term. I'm not going to be needing the definition of that very much. I'm just going to sort of explain the kind of classification that it gives of the different sorts of phenomena that arise, and then sort of use it informally. So what we're going to do is we're just going to assume for simplicity that the monodromy on S is the full symplectic group or orthogonal or symplectic group fixing the bilinear form, the topological bilinear form coming essentially from cup product. And the level is some, quantity associated to a natural Hodge structure on this, the Lie algebra of this monodromy group. Doesn't really matter what it is, but it's an integer, and there's three cases that I want to consider: level 1, 2, and level 3 plus. So level 1, an example of the kind of thing that happens is you can take a universal family of K3 surfaces. What I mean by this, there's no universal family, strictly speaking, of K3 surfaces. I mean a family of polarized K3 surfaces such that every polarized K3 surface occurs as a fiber and occurs at most finitely many times. So this is like, there's sort of standard constructions of these kinds of things. And in this situation, the set of all such Z, or the set of all such loci Z, which essentially correspond to the loci where the K3 surfaces acquire additional line bundles, the set of all loci Z is analytically dense in S. So these loci Z are basically everywhere in an analytically dense way. And what's more is that they're sort of so plentiful that even if you start with the Hodge theoretic data and you start deforming the Hodge structure in such a way, just deforming the direct sum decomposition in such a way that it stays polarized and it contains the vector V, then those deformations all actually occur in the algebrogeometric parameter space. So this is a kind of Shimura variety phenomenon where you have the entire Hodge theoretic moduli space is actually captured by algebrogeometric data. And this is a very special thing. It happens in what I'm calling level 1. Level 2 is sort of less nice, but we still get lots of these loci Z. In level 2, for example, what you can take is you can think of a universal family of degree D hypersurfaces in P3 for D large enough. And in this case, the set of all such loci Z is still analytically dense. There's still a lot of them. This result very often goes by the green density criterion and so on. But it's not true necessarily that a Hodge theoretic deformation, if you deform the Hodge structure in some way, that you'll stay within the algebrogeometric parameter space. Now the Hodge theoretic moduli space, the moduli space of all Hodge structures, is much bigger than the algebrogeometric parameter space. And in level 3+, what will then happen is that there's, first of all, even fewer of these loci Z. And you can actually prove that all of these loci Z lie in a proper Zariski closed subset of S. So they're not analytically dense anymore in particular, and they're not even, the collection of all of them is not even Zariski dense. So there's some finitely many proper algebraic loci which they all lie in. An example of this kind of phenomenon is hypersurfaces in Pn, where you take both D and N to be sufficiently large. And by universal, I mean sort of you just kind of write down the general equation of a hypersurface. Okay, so these are the kinds of 3 things that can happen. And the particular case that I want to focus on for the purpose of this talk is this third one. And what I want to show is I want to explain how we can actually prove the 3+ result on what I'm going to call the integral level. So what do I mean by that? I mean, not only do I want to say that all of these non-trivial families that are in characteristic 0, that come from characteristic 0 families of algebraic cycles, lie in some proper Zariski closed locus. But in fact, if you look at the original family, not the complex algebraic one, but the integral family of hypersurfaces, then there is some proper Zariski closed subscheme of the parameter space that is going to contain not just the characteristic 0 families, but also the positive characteristic ones again, which are also non-trivial in a certain way that I'll make precise. Okay, so before I do that, though, I want to explain how this level 3+ result works. How do we actually prove this result in the complex algebraic setting? And for that, I want to review briefly some facts about Hodge theoretic period maps. So what I'm going to do is we're going to fix some polarized lattice V comma Q. So this you can think of as like you can pick maybe a fiber above a complex point and look at the Betty cohomology with integral coefficients and the associated polarization. And then we're going to take D, the complex manifold D, to be the space of all polarized Hodge structures on that polarized lattice. There's a natural projection from D to D mod gamma, where gamma is all the automorphisms, the integral automorphisms of the lattice which fix the polarization. And D mod gamma you can think of as a moduli space for all polar isomorphism classes of integral polarized Hodge structures on this fixed V comma Q. So the period map, the kind of period map I'm going to talk about, is simply just look at a point in S and send it to the isomorphism class of the polarized Hodge structure above that point. And that's a well-defined analytic map. And we're going to use this to study the Hodge loci. And in particular, what you can then do is, if you take a vector V, like an integral vector in your lattice, you can define a complex submanifold of D, which is the space of all polarized Hodge structures on V comma Q, which consists of Hodge structures for which V lies in the middle piece, right? So you can define this complex submanifold. And the loci Z you can show are obtained as irreducible components of phi inverse pi d sub V. So you project this manifold that describes the Hodge structures that contain a fixed vector. You think about it up to isomorphism, you pull it back, and the analytic components of that are in fact algebraic loci that correspond to these loci Z, the maximal such loci Z over which there exists these families, with the caveat that this is sort of assuming the Hodge conjecture, because you don't actually know that these Hodge classes correspond to algebraic families. They do, but every algebraic family will lie in such a locus. And so there's a recent paper of Baldi, Klingler, Olmo that used this to show the level 3+ result. And I'm going to give a very rough kind of paraphrase of their argument. What they first do is they consider the locus E in S of complex points through which there exists a positive dimensional analytic germ, which looks like phi inverse of D sub V, but for some complex vector. All right, so not necessarily some rational vector, which is what the the kind of Hodge theoretic setting describes. That's what we're really interested in. But they simply consider it, okay, suppose we have this more general thing where we're defining these loci by virtue of some complex class being in the middle piece of the filtration. And what they can then do is there's a kind of whole industry in Hodge theory that has arisen in recent years that studies the kind of tame geometry of these period maps phi. And what you can do with that is to show that when you have these sort of what are called definable analytic conditions, then they will actually end up defining algebraic loci. And so in particular, E, or if you like the closure of E, if you're worried about it not being a closed analytic closed subset, is an algebraic subvariety of S. Okay. And so really what you then have to show, because you're just trying to show that all these loci you care about lie in a proper algebraic subvariety of S, you have to show that E is not equal to all of S, right? That's all you have to show. And this you use the level 3+ assumption. And what you do is you pick a very generic point of S, some generic point of S, and then you look at how the period image of S intersects these D sub V's for some V that you expect to be there. And what you can show is that this intersection actually has to be larger than you would expect from computing the codimensions of the image of S and the codimension of D sub V and V alone. The reason that these intersections are kind of larger than you would expect come essentially from Griffith's transversality constraints, if you're familiar with the Hodge theory. And so there's some theorems in Hodge theoretic functional transcendence, in particular the Ax-Shanuel theorem, that show that at a generic point of S, this can't happen. Really, the only place that you intersect these kind of very special algebraically defined loci in the Hodge theoretic moduli space, and the only way that they intersect, you get this large of an intersection with the period image, is if that point S actually lies inside some kind of locus that's defined by maybe a possibly higher order Hodge tensor in some power or something. But it's really can't happen at a generic point of S. And that shows you that E is actually a proper subvariety. Okay, and so what I want to do, my goal is to really explain how you can actually introduce new tools to make this sort of argument in positive characteristics.
Interrupt you for a quick question. In this argument, the level 3+, does it only come in the last step? So for the algebraicity, the level is not improved.
That's right. Yeah. So for the previous steps, the level is not used.
Thank you.
Okay. So I want to then now explain basically how we can do the same kind of thing in positive characteristic by introducing some new tools. And in order to do that, I'm going to have to reinterpret all the things I've been saying about monodromy. I mean, you can talk about monodromy in positive characteristic, but not in a kind of nice algebra geometric way. And I want to think of these things a bit differently. And so what I'm going to do is I'm going to use the Riemann-Hilbert correspondence. And what the Riemann-Hilbert correspondence tells you is that every local system on a complex algebraic variety corresponds to some kind of algebraic vector bundle with a flat connection. And in the particular case, for the monodromy representations that we're getting associated to the Betti cohomology of these families, there is a kind of standard algebraic vector bundle with connection, which comes from algebraic Theorem cohomology. So there's this theory due to Grothendieck of algebraic Theorem cohomology. What you do is you form the algebraic Theorem complex, which is sort of the same as the kind of naive Theorem complex. It's a Theorem complex just with algebraic forms. And this doesn't really quite compute the cohomology of the correct cohomology of the algebraic variety or the family of algebraic varieties that you're considering, but you can use derived functor machinery to resolve this complex. And then once you do that, you get a kind of algebro-geometric definition of the cohomology, which admits a comparison map to the analytic Betti cohomology. And so this, in fact, gives us an algebraic vector bundle that kind of describes the cohomology, and we can, it even makes sense integrally if our family X over S is defined over some ring of integers of some kind. Then you also want to consider the connection. The connection has a very explicit algebro-geometric description associated to due to Katz and Oda. And the way this correspondence works is that given a local system, you can tensor with the sheaf of all analytic functions on S. That gives you a vector bundle. You can prove it's algebraic. And the reverse direction goes by starting with the algebraic vector bundle and taking the subsheaf of the analytification given by all flat sections, and that's the local system. Okay, and so under this correspondence, if I have this pi1 z invariant vector v, what that's going to correspond to is a flat section of this algebraic vector bundle. So the way that works is that if you have an invariant vector, then that gives you a global section of the local system. And because the local system is the flat sections, it'll give you a global flat section on the other side. There's also a Hodge filtration and algebraic Hodge filtration on H that I'm going to need later. That's just why I'm mentioning it here. And one kind of observation that you can make, one thing that you can verify from the sort of the definitions or the cohomological machinery, is that actually if you have a family of over positive characteristic, right? So you have, let's say, a smooth projective family y to z of the kind that I was talking about on the previous slide, then even if that's that family is only defined over some finite prime of the ring of integers of the associated to this family, then you're still going to get a flat section. And so this language of flat sections kind of subsumes the two different cases that we're trying to talk about when we're constraining these algebraic cycles. And so let me give you a kind of very naive idea that you might think of about trying with respect to trying to get this sort of strategy, trying to prove this sort of Zariski non-density result integrally. One thing you could try to do is you could try to use a kind of Lefschetz principle. So what do I mean? A Lefschetz principle is some kind of thing where you write down some algebro-geometric conditions that you want to be satisfied. They make sense on some integral level. And then you want to prove something about these algebro-geometric structures. So you base change to the generic fiber, to the characteristic 0. You prove it there. And then general algebro-geometric machinery gets you that it holds away from finitely many primes. And so if we had, for example, some family of subvarieties of S, where we knew that all the families of those, all the fibers of that family corresponded exactly to the loci in S, where we had extra flat sections, or we knew that we were just talking about possibly the subvarieties in some fixed finite family, then we could get what we wanted from characteristic 0, and then conclude it in away from finitely many primes in positive characteristic as well. But we can't do this. And the reason you can't do this is because there's no good way to bound a priori to bound the degrees of the subvarieties Z in S that you want to consider. So there is no kind of family that contains all the different subvarieties of S that you would want to study in order to make this kind of argument work. Or at least we don't know in advance that there is such a family. And so what we then have to do is we have to try to find a kind of different way of applying a sort of Lefschetz argument. And the way I'm going to do that is to try to interpret the existence of these loci in terms of certain kind of infinitesimal differential conditions, and then apply the Lefschetz principle directly to those differential objects, which are going to have some kind of algebra geometric structure associated to them. That may sound a bit imprecise. I'm going to try to make it more precise, but this is a kind of naive intuition for what I want to do. And so the infinitesimal algebra geometric objects that we're going to consider that are going to allow us to do this is what I'm going to call an infinitesimal period map. So if you think about the previous argument I gave you that Baldi, Klingler, and Olmo were doing, they were very heavily using the theory of period maps. Now, in positive characteristic, you can't really construct a period map, right? You can't construct this kind of, it's a very analytic object. But what you can do is you can construct formal solutions to the same system of differential equations that define the period maps. And so what I mean by that is, if you look at the connection, we have this algebra geometric connection, which is this thing that makes sense over the integers. It defines a system of differential equations, the solutions of which are period maps. The way you get that system of differential equations is by fixing some frame on the algebraic vector bundle, which is compatible with the filtration. And then you differentiate that frame and you get a system of differential equations that describes for you how to change that frame into a flat frame. And by writing down that period matrix, basically, you can construct a period map. And that system of differential equations, because the connection is defined integrally, that system of differential equations is also defined integrally. So what we can do is we can simply say a period map, which has up to order R, because there's this positive characteristic issue that you can only consider denominators up to the characteristic of the field. But we call a local infinitesimal period map of order R, which I'm going to abbreviate to an R-limp, is a formal solution to this system of differential equations that we get. By a formal solution, I just mean that instead of taking a full power series solution, you truncate it at order R. And R is going to always be smaller than the characteristic that we're considering. And these maps are really ultimately algebra geometric objects because they're just formal maps. And we can then use them to define some loci integrally inside the base. And in order to define these loci, we're going to introduce a kind of some jet theoretic tools. So one way of sort of making sense of what it means to have a kind of infinitesimal analytic locus in like an algebra geometric setting is to think of such a thing as a map from the formal d-dimensional disk of order R into the space. So if you have any space X, there is what I'm calling, there's a jet scheme of d-dimensional disks of order R associated to X. The formal definition is it's the scheme that represents this functor that I'm writing here. One way of thinking about it is simply, if you just imagine, let's say you're in a fine space, you imagine writing down a general map from the d-dimensional disk of order R, this formal infinitesimal disk, to the affine space. And let's say your variety is defined by some algebraic equations in that affine space. What you do is you just write down the conditions that d-dimensional map lands inside the subvariety. And that gives you some algebraic equations on the coefficients of this map. And those algebraic equations define the jet scheme. So we're parameterizing all maps from an infinitesimal d-dimensional disk of order R into our space. And using this data, which I have the algebraic vector bundle, the filtration, and the connection. And assuming that R is invertible in our field or over our ring, you can use the differential equations that describe these infinitesimal local period maps, these R-limps, to construct evaluation maps, which will take a disk, an infinitesimal disk, which I'm representing here by a jet, and compose that map from the infinitesimal disk to S with the infinitesimal order R period map. And you will get an element of some flag variety, because remember, the infinitesimal period maps send points to flag varieties, and all the differential information around that point to differential information around in the direction of in the directions around the flag that you land on. And so using this data, you can construct at a kind of infinitesimal level an evaluation map, which will take for you an infinitesimal disk at some point. And if you also give it an initial condition, which defines for you a solution to this system of differential equations, it'll output for you another infinitesimal disk, which is the image of the local period map with that initial condition and on that disk. Okay. And this is the kind of key technical tool that allows us to describe, to do a kind of integral version of the argument that I described a few slides ago. It's probably the most confusing thing I'm going to say. So if there's any questions about that, then I'm happy to take them now. Okay. All right, so we have these evaluation maps that allow us to evaluate these infinitesimal period maps on infinitesimal disks. And now we can give a kind of integral version of the previous argument. So instead of considering the analytic manifold D, we can't talk about this analytic manifold because we're not in an analytic world, we're in an algebra geometric world. We can work with a flag variety that I'm going to call check L. And instead of considering these loci D sub V, you can consider these analogous loci L sub V. The difference between these two things is that when we talked about the complex analytical manifold D, we were considering Hodge structures, which are really the Hodge decomposition of the associated complex vector space. And the flag variety check L is we're considering the flag, the Hodge flag that you get by adding up sort of the summands iteratively. And that's an algebra geometric thing, whereas the complex manifold also has some polarization conditions that are analytic. And so one is larger than the other, but we can do the same sort of thing where we just map to the flag variety instead, and we pull back these loci check sub LV. And then we're going to construct these constructible subsets of the scheme S. So S is some scheme defined over a ring of integers, maybe of some number field, maybe with some associated, with some additional denominators. And we're going to construct using this a constructible subset with the following condition. So there exists some infinitesimal period map of ordered R defined by the initial condition M at S. So if S is a point in this constructible subset, there exists some infinitesimal period map defined at S. I wrote here a complex vector. It really shouldn't be a complex vector. It should just be some vector defined over the same field as the point S. And a jet defined at S such that if you evaluate the infinitesimal period map on that jet, which remember represents an infinitesimal disk, then you land inside that flag subvariety. And the point is that if you take a D sort of large enough, so like if the period map is quasi-finite, then you can take D equals 1, for instance, then the intersection over R, all R, of the complexification of these loci agrees with the locus E in the Baldi-Klingler-Olmo argument. And what they showed is that that locus E was a proper Zariski closed subset. And so if you think about what this means, the only way that you can have a descending intersection of constructible algebraic sets that eventually lies inside a Zariski closed subset is if for some R, that one of those actually is a proper Zariski closed subset. And what you then do is that you say that, okay, away from finitely many primes, because these constructible loci are defined using finitely many pieces, and there's away from finitely many primes, it agrees with the generic fiber. You get the Zariski non-density result on the integral level as well. Okay. So there's one other thing that you have to do to make this argument work. I mean, I've described using these period maps. I actually have to relate these period maps to algebraic cycles, right? Because I'm telling you that these loci constrain algebraic cycles and families of algebraic cycles, but otherwise it's just some weird loci with some infinitesimal period maps. So there are several ways to do this. So there's at least two ways to do this. One is that there's this Hodge flag on the algebraic Theorem cohomology that I was talking about. And you can actually show just by for example, from the usual Chern class theory, that if you have a family of algebraic cycles, it's not just that they induce a global section of this algebraic vector bundle, but they induce a flat section which lies inside the so-called middle filtered piece, or it lies inside Fk, where the weight of the filtration on H is 2k. And this will actually constrain the differential system for psi, because if you remember how we constructed psi, it wasn't just, we started with a filtration compatible frame, right? We're parameterizing these flags, and those frames are constrained if, some of there's some flat sections inside one of the filtered pieces. And another fancier way you can relate these loci to algebraic cycles is using crystalline cohomology. So there's this very sort of sophisticated formalism of crystalline cohomology, which tells you that if you have such a y lying over z, then you can look at this crystal on the crystalline site associated to the locus z. And these crystals are very sort of special objects in sort of the crystalline formalism that always have with them an associated connection. And there's a very sophisticated kind of point of view on the connection that you get from pushing forward the crystalline structure sheaf on X down to S, which tells you that actually once you restrict this connection to Z itself, you get exactly the Gauss-Menen connection. I'm not going to go into the details of how this works, but the point I want to emphasize here is that the crystalline machinery actually gives you a kind of way of interpreting Hodge loci mod P. So what I mean by that is that in characteristic 0, there's this kind of separation between a locus defined by algebraic cycles and a locus defined by Hodge vectors. Conjecturally, they're the same thing due to the Hodge conjecture, but one is in principle larger than the other, because whenever you have a family of algebraic cycles, you can show that there's a family of Hodge vectors, but not vice versa. And so here, what you can do is you can describe a kind of more general setting where you can just talk about certain Galois invariant for like the Frobenius action vectors that are conjecturally come from families of algebraic cycles. And you can actually show that even these kind of conjectural loci lie in the locus in the previous argument. So it gives you more than just constraining. In principle, they're the same thing, but you can constrain loci that you don't even know that they're defined by families of algebraic cycles. You just believe that they are. Okay. So just to give you a very kind of concrete version of what we've proved, or one of the things that you can prove with this argument, here's a theorem that this argument proves. Suppose you have f to x to s is the universal family of hypersurfaces in Pn+1 of degree d over the integers, and then assume that the variation of Hodge structure in degree 2 to the k, so k here is the middle cohomology, so it's so I'm assuming that you choose n and d such that this is even, and suppose that that variation has level at least 3. Then there exists a proper closed subscheme E such inside S, where whenever you have a smooth locally closed subscheme Z and a family of this type, one of the following 3 things is going to happen. Either the cohomology classes induced by Y lie in the invariant algebra associated to the cup product pairing. So what do I mean by that? I mean that there are some algebraic cycles that are already defined over all of S, right? That come from cup product and certain other invariants, cohomological invariants that you get over all of S. So you're either getting one of those, in which case you're getting nothing new, or Z lies in this locus E, or Z lies in a GLM orbit in S. So what do I mean by that? I mean that if you are familiar with how these variations of Hodge structure work, if you think about like a hypersurface, right? There's an action, a natural action on the equations of a hypersurface that you get just from acting with a linear transformation on the polynomial that defines the hypersurface, and that'll give you an isomorphic hypersurface. And the Hodge theory is the same, and so on. And so the period map really factors through the quotient of S divided by this group, this GLM action. And so really what you're getting is that, okay, if Z already lied in one of these fibers, then sure, nothing is varying on Z. And so we're not talking about a non-trivial family. So it's either one of these three things, you know, either you get classes that already existed over all of S, you're in a fiber where there's no Hodge theory, nothing's varying, or the cohomology doesn't vary because everything's isomorphic, or you have Z is in this proper locus E. Okay. So one other thing I want to mention briefly before finishing is what can be said about the tensor case. If you actually go to the Baldi-Klingler-Omo paper, they consider the more general setting where you have this family where you're maybe not just considering algebraic cycles that lie in cohomological objects associated to S, but lie in self-products of S with its X with itself, for instance. And the arguments also work to constrain these loci as well. However, there is a kind of additional complication that arises, right? And the complication that arises is in this step where I said that, okay, this locus that I'm talking about, mod P, I can identify its generic fiber with the Hodge theoretic locus where we fix a single vector. That's something you can do when you're just talking about having a single vector that's fixed, or a single vector constraining the flag. But what can happen is that mod P, there's all sorts of additional sort of behavior that when you look at, for example, collections of cycles, collections of tensors that are invariant under the Frobenius automorphism, it's not obvious that those collections of tensors somehow correspond to some other collections of tensors that are associated to some Hodge structure, right? It's difficult in the case where you have many different tensors that you're talking about to relate the kind of positive characteristic and characteristic zero world. And so, like, one of the things that you might want, what you have in the characteristic zero setting is that these loci, as you know, for n arbitrarily large, only come from finitely many analytic families of loci d prime and d. This ultimately comes from the fact that there's finitely many complex conjugacy classes of Mumford-Tate group, for instance. And that comes from the fact that these groups are reductive and have a special structure and things like this. So the Hodge theoretic setting, the algebraic cycles, the kind of conjecturally algebraic cycles are more constrained and belong to finitely many families of loci in this moduli space of Hodge structures. But there's no analog of this fact in characteristic P. And so what you end up having to do is you have to study sort of more specialized situations. And I mean, I have some results on that. I'm sort of still writing them up. But I just wanted to mention this kind of additional complication that comes up when you generalize this method to higher tensors. And so there's kind of there's a few different approaches to this, right? One is you can start fixing some bounded family of subvarieties in check L. So you can say, okay, I'm not going to consider all of the different tensors that I can get, but I'm going to consider some special ones that I really want to study. And then I can define those same loci, Z, which where some infinitesimal period map lands in one of these subvarieties of this inside this fixed family of subvarieties in check L. And this you can do, and then you have to study those families and show that actually the intersection condition that was previously coming from level 3+ is also satisfied in this situation. And you can very often do that. And the other thing that you can do, as I sort of mentioned, is you can try to lift the cohomological data from characteristic P to characteristic 0 and argue that because you have this kind of boundedness in characteristic 0, then you also have it mod P. Okay, so that's what I wanted to say.